the carrier density is determined by two things. It's determined by the density of states, and it's also determined by the probability of occupation. Remember, carrier density is really key to understanding what happens with the electronic properties of these semiconductors. So remember that the density of states, or DOS for short, G of E, in semiconductors looks something like this. So here's energy, here's G of E, and then here we have the density of states for the conduction band, and we also have the density of states for the valence band. So I mentioned to you that the carrier density also is determined by the probability of a state being occupied. So electrons follow Fermi-Dirac statistics, and that really drives this probability function. And so let me draw that for you. So we notate this as f of e. And so here, what I'm drawing for you is I'm drawing for you as a function of energy, I'm drawing f of e. So here, here we have we'll have something that looks like this, where this is 1, and so this is f of e. Okay, so we'll come back to understanding where this probability comes from and how you describe this. But if you want to get to the number of carriers, which if you're like me is what you're after, then n or p, so the number of electrons or the number of holes, which are the number of carriers, this is simply equal to an integral of G of E, so that's the number of states that are available at a given energy, times f of E dE. So essentially what I'm telling you is that we actually need to multiply these two functions together in order, and then integrate them. And so if I plot for you, if I sketch for you what this would look like, this will look something like this. Here's E, and essentially we'll end up with this is N of E, and then we'll also end up with a P of E, so the number of holes as a function of energy, and then we can integrate over whatever energy we want in order to get that number. The other thing I just want to note is that impurities add additional carriers by creating states in the band gap, but they do not change the density of states. So let's talk more in depth about how we actually calculate this. So if I want to write down exact expressions for the electron and the hole densities, what I would write down for electrons is that n of t is equal to, and here I'm going to integrate because I really want to know the number of electrons in the conduction band. So I'm going to start summing up at the conduction band, and I'm going to go up to infinity. So we're going to have dE, we'll have gC of E, so this is the density of states in the conduction band, and then F of E. We can write down a similar expression for the whole concentration as a function of temperature. And so here, what we're going to do is we're going to integrate up to the top of the valence band, and we're going to go from minus infinity to the top of the valence band. And so again, we're going to have dE, we're going to have V of E, which is the density of states in the valence band, and F of E. So that's it. It's simple, right? Well, not so fast. It involves a few more details, and so let me get to that. So one of the first things that I didn't tell you is I didn't tell you what F of E is. So F of E is the probability of occupation. As I said, when you fill up electronic states in a solid with electrons, it's like filling up a bathtub with water. That's essentially what happens. You have a spin up and a spin down electron per state, then that's full, and then you need to move to the next state. So the key here is that you can't have all the electrons in like the absolute lowest level. They fill up according to these Fermi-Dirac statistics. And so F of E, which are the Fermi-Dirac statistics, this is equal to 1 over exponential of E minus EF over K BT plus 1. I think we'll have to cut.